recording should have started. It automatically disables cameras, so if you want to turn them back on, you can. And yeah, maybe I do a short intro because we are not that many people here, but yeah, maybe some people watch the recording. So yeah, today is the second interim meeting of the Energy Fault Detector challenge on the We Go Win community. And yeah, the interim meeting is basically there for discussion of different solution approaches and for yeah, especially exchanging different ideas and improving on them. But since we are only yeah 3 people here and 2 from Fraunhofer side, we will just see yeah Fahad's presentation of his approach. He's currently the leader in the challenge with a good margin. Has a 0.72 score in the public leaderboard, and yeah, I would say the stage is yours. You can present your thoughts behind the approach, and we will give some feedback and to it. You are currently muted.
Oh, sorry. Thanks a lot, Christian, for giving me the opportunity. I will share my screen now. Guys, can you see my screen?
Yeah, it's visible.
Our model is like a hybrid model. So it's combining physical modeling with the machine learning. So this is the title of our our model. So starting with the flow chart. So this is the steps we are following. So in SCADA, so in the K data set, it is mentioned like the status may be faulty. Like we can like improve them by using the power curve. And then I have determined the power curve. So for power curve, we need 3 things: the cut-in wind speed, rated power, and also the rated wind speed. After doing the power curve, we have to optimize the for developing the ideal power curve, we need optimized pitch angle, which is like -2 to 5 degree, because if the pitch angle increases, the power decreases. So I developed the power curve for the ideal pitch angle and also in consideration with relative wind direction. This data is available in the K data set. And then we have analyzed the wake effects. So we have 3 wind farms available, A, B, and C, and they are different turbines. And each turbine has different data sets. So if we look at the turbine, not all the turbines are placed in the front row. Some of them must be placed in the second row. And if some wind turbine is placed in the second row, there's gonna be some wake effect. The power won't be same as the turbine in the front row because of the wake effect. Then we have determined the wind farm layout, like how turbines should be placed. And then we have developed different threshold status codes based on the positioning or the wind farm layout. And then we have reconstructed the status labels. And afterwards, once the status are redefined or reconfigured, we have used a machine learning model like a classifier, light GBM. And now I will go into details. So I have already mentioned like we have used power curve for making the status more accurate, and starting with the power. So this is the power curve formulation. So if we plot power, I have used active power here, and wind speed, our curve would look something like that. So the cut-in speed is the speed at which the turbines start producing power. In most wind turbines in industrial standard, the cut-in speed is mostly 3 meters per second. And for rated wind speed, we have a range from 10 to 12. So this is a formula I have used, like 99 or 98% of the maximum power would be my rated power. I have kept a margin of 2% because there may be some errors. So once my power curve is generated, I have to do the wake effect modeling. As I have told you, like there are different turbines. So the power produced by some turbines would be lesser. and I have used this formula of power to rated power ratio to determine the wake effect. I can show you like this. For example, this is for wind turbine C, wind farm C. You can see like for wind turbine 2, the power to rated power ratio is very high. It means like the wake effect would be minimum here, suggesting it should be in the front row. And for wind turbine 32, the the power to rated power ratio is slightly less, indicating some wake effect. And then for wind farm C, my layout looks something like that. So wind turbine 252 should be in the front row, center row, and the back row. I will show you how much threshold confidence I have kept here in detail after, I think, the next slide. Okay, so we have 3 rows for wind farm C, and these are the codes we have used. As I have told you earlier, I have created an ideal power curve. So in case of front row, we have to use 100% power curve. So anything which is above here, I can show you like this. So this is the dotted black line. This is my ideal power curve. Anything which is like on the left side should be considered status zero, like a normal condition. And anything on the right side should be considered as the abnormal condition, only for the ideal pitch angle. Uh, Similarly, for center row, I have added a threshold of 2%. And for the last row, I have added a threshold of 5% based on the wake effect. So if we are in the center row, this black line, the ideal power curve would move a little to the right. So more normal status should be considered. And after considering it, I have applied to my training data set, and my status looks something like that. So green shows normal, blue shows abnormal. And also one more important point is the different status. So 0 to 5. If we look in the definition of status 4 and 5, it shows like the service team is carrying out maintenance activity, which suggests like power ideally should be 0. If some maintenance team is there, power, the wind turbine won't be operating. So we have to consider that in mind as well. And for different pitch angles, like you can see, I have created the ideal power curve for the ideal pitch angle. For different pitch angle, I have used the cosine function so that more normal points should be considered for the different pitch angle, because when the pitch angle increases, the power production decreases. Although I don't have the, although there's a ideal formula for the pitch angle uh, based on the power production, but we have limited data available. For example, I need the rotor diameter, rotational speed, uh, which was not available to me. So I have used the cubic cosine function. So in this way, you can see the status 0 and status 5, they are redefined now. As compared to the original data set, it is now redefined like this. And afterwards, uh, I have used binary classification. So I have used status 0 for the abnormal, and status 5 also includes status 4, status 3, and all the other statuses as well. So I only have two status, normal versus abnormal. And then I have used simply a classifier like GBM. I have used previously used different classifier like random forest, XGBoost, but on the basis of R1 score and F1 score, F1 score and accuracy, light GBM was performing the best, so I stick with this. And also I have used prediction smoothing parameters. So instead of giving me 0 and 1 for a time lapse, for a time event, it is giving me a prediction like 80% or 20%. Like 80%, there are chances of being normal, 20% being abnormal. Then we have to use the value from previous values as well. So it become a weighted average. And this is the next step. I have also determined the component which are about to fail. So I have developed a predictive maintenance regime. It has nothing to do with the competition, but it's a new step. And I'm sure like we can further improve this methodology if we know the exact turbine layout, and so that a wake effect can be applied in a more systematic manner, and we can further improve the result. That's it from my side. Sorry, I think I speak a bit too quick, but if you have any question, I can go into details. Thanks.
Yes, thank you very much for the presentation. First of all, I don't think that you speak too fast. It was very well presented, and yeah, I could follow the presentation very well. Um, yeah, and uh, yeah, a few questions come to mind when seeing the presentation. First of all, you refined these status values so that you have a normal you have a new define as you define what is normal and what is not normal in another way. How many normal samples has your model left to learn on, or how do what size is the training data set for your classifier?
So sorry, can you please repeat? I was like writing it down on my notebook, so I miss it.
Yeah, you define the status values in a new way. And so you still have a status value for this is normal operation, and you have status values for this is not normal operation. I assume that your classifier also then gets a portion of normal samples to learn on and a portion of not normal samples to differentiate and classify. So how big is the portion of normal samples that are left after your filtering of yeah, the data?
Okay. There are 95 data sets. For each data set, I do the status reconfiguration
Mhm,
only for the training data. So in that data set, you have mentioned training data set and the prediction data set. Most of the data was normal. Like I think 75% was normal and 25% was abnormal after status reconfiguration. So I just put the whole data in the classifier in the for the prediction time frame.
mhm,
So it learns from the training data set, okay, this is abnormal, this is normal, and then it performs the classification. But I can assure you like
mhm,
it aligns with the care data set like 80%. It's the same like you have mentioned in your you have provided in me in the care data set, but 20% there are changes. So if I check like the care data set normal points and my normal points, they're gonna be a little bit difference.
mhm. Okay, yeah, because I just asked this question because I don't see then I don't see a reason for why, for example, you could not apply the energy fault detector to it. So this would then be a suggestion because at first when I saw your plots, I thought there were only very few points left that are actually classified as normal still. But since it is 75% of the training data that is still remaining, I would see good chances for yeah, using the autoencoder approach from the energy fault detector, which maybe can even further improve your results. Of course, there would have to be some kind of hyperparameter optimization, maybe. But there are also example scripts within the package which can yeah, make this process of applying it easier and optimizing it. I know you don't have that much time to spend for the challenge, but yeah, if you are interested, would be also really interesting. And I think, yeah, um, maybe it
So
could even further improve your score.
yeah, so Christian, I can now I got your point more clearly. So I can show you once again. I think you get confused like by the graph, by this graph, but these
Mm,
points are too much. Like they are densely packed here, many
mm,
points. So the graph maybe is not showing you the exact thing.
mm,
So these points looks very big data, but these points are like confined, like all the data
mm.
points are here, like so they are too much many and on the same points.
Yeah. Hmm.
So that's why, yeah. And also, I think this is for one particular data set of a particular wind turbine. Maybe it was behaving abnormally. So if I
Hmm.
show you the graph for a normal data set, uh, they're gonna be very fewer points on the right side.
Hmm.
Maybe, maybe I have an additional question regarding your labeling. If I understand it correct, you define the normal and abnormal status for the training data, right? How do you proceed with the prediction? I think you said every time if the pitch angle, so if the turbine pitches, it is abnormal, correct?
No. So for the ideal power curve, I have used an ideal pitch angle, which is -5 to 2 degree. So
Yeah.
once my ideal power curve is generated, for the other pitch angles, like if we have 20-degree pitch angle, then automatically the power production won't be following the ideal power curve. For each pitch angle, we have to design a different ideal power curve for different pitch angles. So instead of creating it, I use a cosine function to add a threshold.
Mhm.
So for example, if we have a pitch angle of 20 degree and we have a particular wind speed and our power should be like 100. Now, if even the power is 80 megawatt or kilowatt, it should be considered normal as well. So we have added a threshold for the pitch angles.
Yeah, okay. Is this threshold considering the power? So that means do you have used it to filter your normal your training data, but what happens if you have in the prediction a sample where you have the pitch angle higher your threshold, but the reason is only curtailment? Is that then not considered in a prediction, or is it by this rule defined as abnormal, or how do you proceed with that?
Uh, in our training data set, we have different pitch angles available from 0 to 90 degree. There are some
Yeah.
negative angles as well. So we can say -5 to 90 degrees. So for the status reconfiguration, we have applied -5 to 90 degree for the training data set. So it will like automatically consider which is normal, which is abnormal based on the pitch angle threshold as well. So firstly, we have an ideal power curve. Then we have different pitch angles, which we have added a threshold, like to consider these points are also normal. And in coming to the prediction, there are also different pitch angles. So I'm doing nothing with the prediction. The light GBM classifier automatically sees the pitch angle, sees the power values, the wind speed, and it determines either it's gonna be normal or abnormal. So uh, that's it. And also there's a point like whenever the pitch angle is higher, maybe 90 or 85, it shows maintenance should be carried out. Because when the pitch angle is 90, power automatically becomes zero. It's a basic training in wind turbine operation. Whenever they want to stop the wind turbine, they increase the pitch angle to 90. So 90 or 85, so that the power production would be almost equal to zero. So for status 3 and 4, it closely aligns uh, with the pitch angle. But in the K data set, I have seen some status value 3 and 4, but the pitch angle is 0 or 5, which shows like there may be some faulty status reconfiguration in the K data set.
Ah, okay. You use it only for reconfiguration of these status codes,
Yeah,
not
exactly.
for filtering your predictions later
No,
or
no.
labeling your predictions.
No, it's only for the training data set. I only reconfigure the status and nothing else.
Ah, okay. Okay.
So
So
your
there is no post-processing steps. There's only pre-processing steps, and I'm only changing one column of the K data set, which is the status.
Okay.
and so
Oh, I see.
you basically your light GBM model is like 5 normal behavior models in one, right? Because it learns the normal behavior for 5 different modes of pitch angle configurations or whatever, how many different modes you defined. Okay.
Yeah, so I'm not sure like how my classifier is working, but there's a column in the K data set which shows the pitch angle.
Mm.
But I'm not changing it in my training or prediction. It remains the same. My only goal is to reconfigure the status.
Yeah.
So if I see like there is a normal status and it's not following our criteria, so in pre-processing we change it to either normal or abnormal. And my light GBM, and then we change it the status for to normal and abnormal only. Instead of having 5 status 0 to 5, we are only dealing with normal and abnormal. And then light GBM classifier learns and applies accordingly.
Mm.
Okay. Really interesting that this little change makes so much difference.
Mhm. And it would also, I kind of revert my comment with the energy fault detector from before, because I think it would not be that straightforward to apply it to this refined data. Only if you can really divide status back into normal and not normal. But if you have the ability to create models for different operation modes of the turbine, so for differently rated or curtailed operation modes, then you would actually have to train multiple normal behavior models or encode the status kind of give condition the model on the status more. I would say because that would be valuable information for the autoencoder. So you could just apply it to normal and not normal status and use your refined status as a normal index as it is defined in the energy fault detector. But maybe it would also be very promising to use it as to use your further insights into the status as a condition for the autoencoder to even be more more precise. So yeah, a lot of ideas come to mind when with your additional information that you generated from the data. So yeah.
And also one more point, like I'm considering the turbine layout. So um, if we look into the data, there gonna be different turbine IDs, and each turbine ID consists of 5 or 6 data set. So we don't have to change the data set, but we should know like where the turbine should be placed. Once we have that turbine layout, I have added a wake effect as well. So it consider other normal points as well. So we have an ideal power curve, but we increase add a threshold as well. Like if a turbine is on the second row, there gonna be some wake effect. So we have to consider it as well.
Mm-hmm.
I think wake effect is improving the result quite a bit.
Mm-hmm. Yeah, I think so too. That's also a thing that we did not that we did not yet capture or that we did not use for our anomaly detection yet. So yeah, this could very well be what makes a big difference in the score. Yeah. Okay. So yeah, I'm out of questions. Maybe, Florian, do you have further questions or?
I think not, no.
Okay. Then yeah, unfortunately, no one else joined. Although we had a other team that was wanting to present their yeah procedures here, but yeah, I think instead of that we got a very well structured presentation from Part, and yeah, that's very nice, and we could discuss it in detail. If someone yeah watches the recording of this meeting, they can really take a lot from that and learn from that. And if no one does it, then I think yeah, it will be very hard to beat your approach.
No,
Yeah.
I'm very positive. Like if the geotech team, the team on the second position, they are doing wonderful. And if they use the pre-processing steps, I think they can beat me. But finger cross. It's just a competition, and I really want them to um, like outperform me. It's totally fine. But I think if they use the pre-processing steps, they have the potential.
Mhm. Okay. Yeah. Then yeah, thank you again for the presentation. I would start the recording now. Then or maybe one question before. Do you have any questions for the yeah the competition or regarding the data set or approach or whatever?
Yeah. So Christian, I have created whole code and my whole detailed methodology in
Mhm.
GitHub. I have shown you, but I have made it private right now.
Mhm.
So once the competition is over, I can make it public and we
Mhm.
can discuss like how further we can improve it, because I'm sure like if we implement this approach to SCADA,
Mhm.
because in SCADA they don't have the status uh, configuration. So on the basis of status or something like that, we can predict which component is about to fail. And doing some vibration analysis, we can also provide some incentives about which kind of actions or preventive actions we have to take. I have also developed a predictive maintenance regime. So uh, uh, it's available on my GitHub as well as on my thesis report. So if in future, if you want to work on this idea, I would be glad to join the team.
Mhm. Okay. Yeah. So yeah, it's also very reasonable to set the GitHub to private, so that it's not just copies. That would be
Yeah.
yeah a shame. And yeah, we will definitely yeah have a look at the repository after the competition. It contains yeah really interesting stuff, and we are definitely considering yeah adding it to the energy fault detector and to the pre-processing if we are allowed to. And yeah, it's a really yeah a really cool new insight that we did not consider before. So it's also something that we hoped would come out of this challenge. So it's nice to see that. Yeah. Okay, then I stop the recording here. Okay, there.